Today I want to talk about some conceptual problem in the context of black hole entropy. And when you look at the computation of the gravitational partition function in Euclidean quantum gravity, as done by Gibbons and Hawking, you realize that there is the contribution to the log of the partition function from the Euclidean action evaluated at the black hole solution. And in fact, this contribution is the contribution that gives the classical black hole thermodynamics. And then there is the usual contribution of the thermal gravitons, which you understand well because you know what the degrees of freedom are. But at least from what I can tell, there is no real understanding of what Hilbert space gives rise to this contribution to the partition function. So there is another way of phrasing the question is, can you do the trace on the left-hand side explicitly when you know the Hilbert space in which to do this? And maybe since gravity is a complicated nonlinear problem, maybe one can first ask, and since this is a conceptual question, is what is the simplest model in which you can do this computation, meaning the Gibbons-Hawking, compute the Gibbons-Hawking contribution, and then do explicitly the microscopic computation and compute the trace in a suitable Hilbert space. So I will not do gravity, I will do a very simple model for this. And the question is, what is the simplest model? And so, of course, the simplest model is a linear theory, instead of doing this complicated nonlinear thing. And the linear theory I'm going to choose to do the computation is electromagnetism. Of course, you can complain and say this is, of course, much too easy and will tell you nothing about gravity. But maybe you are right, but then maybe the problem is interesting on its own, and one can think about it. And I still believe that if you understand the linear theory well, you maybe can also say something about full gravity. It's, in my mind, there's absolutely no doubt that at least in linearized gravity, you can do exactly the same. If you can do it in full gravity, that's maybe not so clear. Yes, you can do that as well. But you see, no, my talk, okay, good. My talk is about the background itself. Okay? For instance, here it would be linearized gravity about the black hole solution, right? But my talk is about the background itself. Can you understand the microstates for the background in a simple linear model? So for instance, in Chern-Simons theory, in any of these theories, you compute the partition function, and there's always this contribution which you get from the classical Euclidean action with suitable boundary terms that you evaluate at the background, and that gives a contribution to the partition function. And my question is, in a simple model, can you understand what are the degrees of freedom for this classical contribution to the partition function? That's the question. Is it clear? The other one comes on top, of course. But and my classical solution, which is the analog of the black hole solution in electromagnetism, is the Coulomb solution. That's what I'm going to use as the analog in my model. Okay. Okay, and the model I'm going to consider, as I just told you now, is the Coulomb solution. So I take either two concentric, so it's a very simple Freshman problem. So you take two perfectly conducting spherical shells, which have charge plus q and charge minus q. And you take the region finite. And then you know, of course, that in between the shells, you have the longitudinal electric field, okay, which goes like 1 over r. The question is, so either you can do this spherically symmetric problem, or you can do the analog planar problem, where you take two perfectly conducting planes of charge plus q and minus q, separated by a distance L3. And then, of course, the potential is linear in Z, and the electric field, the longitudinal electric field is constant. So this is my background solution, okay? And I want to understand the microstates of this contribution. So what you can do in this case is you can try to repeat the Gibbons-Hawking argument for exactly this configuration. And of course, you know everything. You know the classical action, the electromagnetic action with the constraints. There's in between the shells, there's absolutely no source. And all the sources, all the interaction of the electromagnetic field with the charged shells, what is interesting is you can take them into account through the boundary conditions of the problem, as you will see. Okay? So you repeat the Gibbons-Hawking computation in this case. And there is, like usual in this Gibbons-Hawking computation, you have to decide what you keep fixed. So either you can work at fixed potential, and then you have to add a boundary term to your action. Or you work at fixed charge, and then you don't need to add the boundary term to the action. And then you need, when you compute the classical contribution to the partition function, if you go over to fixed potential, you do the standard Legendre transform to get back to fixed potential. So if you work at fixed potential, which is the analog of working at fixed temperature, you need a boundary term, and the boundary term is basically the potential times the electric charge that you have to add to the action principle. You evaluate this Euclidean action on this solution, and you get the Gibbons-Hawking contribution in this case, which goes for the spherical case, it goes like this. So this is the mu dependence. Mu is the chemical potential for electric charge. And you find that the mu-dependent contribution to the partition function goes with the area of the plates in the planar case. And it goes with 1 over L3, the difference in this thing. OK, so this is the analog of their computation for this model. And the question is, can we do a microscopic computation and recover this result? That's the question that I want to address. Any question on this? OK. So what took me a long time, which is of course completely stupid to realize, is that the interaction of the electromagnetic field is exactly like in the Casimir effect. You have perfectly conducting ideal boundaries. And in the Casimir effect, this kind of boundary conditions have been discussed in all detail, and they just mean that the longitudinal part of the electric field has to be 0, and the transverse part of the magnetic field is 0. And I stress here that I do not want to do a heat kernel computation or anything like that. I really want to do what usually you don't want to do, is a detailed mode expansion in order to control the degrees of freedom of the system. Of course, this you can do in very simple cases. You cannot do it in complicated cases, but in this very simple case, you can do it. And in fact, you can do it easily only for the planar case, because for the planar case, of course, you have Fourier series that you can use. If you try to do the microscopic computation for the spherical case, you need to use Bessel function, and you need to know where the zeros of the Bessel function between the two concentric shells are. But if you do the planar case, things are much easier. And these boundary conditions can be implemented by, of course, by expanding the vector potential and the electric field in the xy direction. So they have to satisfy Dirichlet conditions. So in the Z3 directions, you have Dirichlet condition, which means that you have sinus K3 of Z here. And in the transverse direction, you do the usual continuous mode decomposition. So this is what you have. So these boundary conditions guarantee on the vector potentials guarantee that you have this kind of boundary condition for the physical quantities, which is the electric and the magnetic field.
Excuse me, is it just a version of a Casimir effect?
It's exactly that. It's exactly that with 1 zero mode in addition, which has, in my opinion, not been treated, but it's exactly that. It's completely the Casimir effect in this, with this boundary condition. So these are the boundary conditions of the Casimir effect. And I want to do finite temperature, but I want to recover, and at least I have not seen this, I want to recover this contribution when you turn on the chemical potential for electric charge. Usually in the Casimir effect, you do not put electric charge. You have them neutral, the plates. So if you know that, you already, most of the talk. So what is on top of the Casimir effect is the contribution of a single zero mode, which will give this, this thing. Good. So, boundary condition of the Casimir effect, and you see that the expansion of the A3 and the electric field in the third direction, you have to have Neumann condition. And if you have Neumann conditions on these, you see that you have an additional zero mode here. Okay? This additional zero mode, which does not exist for the fields which have Dirichlet condition. What is interesting in this case of two parallel plates is that this zero mode is a two-dimensional field theory on its own. You see, because it's a zero mode in just one direction, and then you have still the K3 momentum, which gives let's say the transverse momentum, and it's arbitrary in this transverse momentum. Okay, and what you are doing is, you do, because you want to understand degrees of freedom, and sometimes to understand degrees of freedom, it's interesting to go back Hamiltonian and not do, let's say, Lagrangian path integral, which sometimes obscures the degrees of freedom that are in the game. So you put the mode expansion in the canonical Hamiltonian, including the boundary condition, and then only you do Dirac analysis. Because then you can tell what are the physical degrees of freedom and what are the other degrees of freedom. So when you look at the constraints, you see that the constraints of the theory, so you start the Dirac analysis by putting the mode expansion into this with the boundary conditions, and you look at the constraint piece, and you see that the constraint piece tells only something about the non-zero modes. It does not say something about the zero mode, because the constraints are just, as you can see, proportional to k, and well, one cannot read very well, I'm sorry about that. It's n3 bigger than 0. So they do not involve this zero mode at all, in fact. Okay. So for this sector, k3 different from 0, it is, in fact, this sector is exactly the same sector that you have in the standard discussion of the Casimir effect at finite temperature. So there are only two independent polarization, and you do either reduced phase-space quantization, or you put. Well, because I want to do finite temperature. Because I want. Yeah, the zero temperature, of course, you should do as well, but I want to do finite temperature because I want to see this bit here, in fact. I want to see beta. Beta. Okay. Well, when I write the partition function, you will see where it comes in. So, but the modes I'm really interested in are these zero modes because they are in addition. So you look what happens to them. So these zero modes are all physical because they are not affected by the constraints or by any gauge transformation generated by those constraints. And you could think that they are longitudinal because they are constant in the z3 direction. So you can write them as the gradient of something, but this something is not really something you can write because z belongs to a finite interval. So you really see that even though formally they are longitudinal, when you take into account that z is constrained to live on an interval, exactly like in topological field theory, in fact, you see that they are not really longitudinal in this sense. Okay? And you can work out what is the dynamics of the zero modes. So you have the Hamiltonian, you plug it into your starting point electromagnetic Hamiltonian, and you can eliminate the momenta, you can go back to coordinate space if you want, and you see that the dynamics of this zero mode is the dynamics of a massless scalar in 2 dimensions with the coefficient here, which is fixed by the length of by the separation of the plates, if you want. Okay? And so you have this additional scalar field, two-dimensional scalar field in the theory, which you get. So it does not really live on one boundary or on the other boundary, but you really get it from the boundary conditions on both ends of the interval. And there is absolutely no z dependence left, of course. And then you can ask yourself, in this quantum theory, when I quantize all these modes, what is the electric charge observable? And do I have an operator in the theory which is this observable? And the observable, the electric charge observable, is just the zero mode of this zero mode, if you want. Okay? It is the third component of the electric field, the zero mode, even in the transverse direction. So that's the observable that you have to put. And if you look back at it, you have to multiply it by A, and this is how it goes. Okay, and then, of course, the problem is completely linear. I have the Hilbert space now completely decoupled. That's the advantage of this linear model. And, of course, the contribution of a massless scalar in 2 + 1 dimension, I just can take any book and find what is the contribution of the K3 non-zero modes. This is just zeta 3 over pi times the area. And this is what will show up in the Casimir effect, as you will see in a moment. But in addition, there is this transverse, this zero mode of the zero mode, and this corresponds to a free particle. And you can turn on the chemical potential for this free particle, and then you can see that, so you can also compute the partition function of a free particle, and you see from this bit, you really recover the Gibbons-Hawking result of this problem. Okay, so that's, let's say, the main thing of the computation. If you want to do if you want to understand the relation to the Casimir effect at finite temperature, you can ask what is the contribution. So how does the computation go there? You compute the Helmholtz free energy in that case. There is the part at zero temperature, which is just the zero energy contribution, which is the standard Casimir effect that you have here. And then you look at the thermal contribution from this additional scalar, and you take any, I'm not an expert in this literature, but you take any book on finite temperature Casimir effect. I choose one which was easy to penetrate for me, at least. And you look what they get when they do the mode expansion of this, and you see that this piece here is exactly the piece that you get from this additional scalar field here, in fact. Okay, that's exactly this contribution. And then you have the rest of the contribution, which comes from these two polarizations. So this comes with only one polarization. And then there's the rest of the contribution, which comes from the standard two polarizations, which you have to use the fact that, let's say, the K3 momentum is discrete now, and you have to subtract the standard blackbody result in order to get finite answers. Exactly like you have to subtract the contribution of empty space to get a non-trivial answer here from this point of view. So this is the contribution that you get from the scalar, and this is the contribution that you get from the other two polarizations at K3 different from 0, and after subtracting the result for empty space. Okay, so it's of course a conceptual computation, it's a trivial computation, but then the claim is that, well, the more interesting claim, well, I would say that a concrete computation is also interesting, but let's say the problem that you really want to address is a problem in gravity, and the claim would be that also in gravity there is a sector, a topological sector, which could give this black hole entropy, and that it should not be related to physical gravitons. Of course, in this case, everything interacts and things is more complicated, but I still believe that there could be something to that picture. Also, the lesson that one can learn, which maybe one wouldn't need to have stressed in the old times, but now that people do not necessarily Hamiltonian analysis in detail, is that one can only decide what the physical degrees of a system, of a gauge system, really are after taking the boundary conditions into account, not before. So you cannot decide in empty space what the physical degrees of freedom are, only transverse photons and so on, and then put boundary conditions and be surprised that things do not match to some extent. Let me, so how much, well, I still have a lot of time left. I think that in all these arguments, because you use path integral arguments, everything is mixed up. You would have A0 also in the path integral if you want, and it's very difficult to disentangle what the degrees of freedom are in this case. So it's hard to say what contribution comes from what sector, I would say. Well, that's why this is both a trivial example, because you can disentangle everything, but at least it's interesting because you can see that there's this topological field theory hiding in the gauge sector of gravity, and that's what I'm going to try to show a bit better. Okay, I have no better answer to the ADS-C picture, I have to say. Okay, let me try to stress the point from another point of view. So here I have showed you reduced phase space quantization. Of course, one can do Berestey quantization, and if one does that, and this is not completely surprising, the gauge sector of electromagnetism is in fact the topological field theory, which will contribute when you have non-trivial topology in the problem. And then I will maybe talk about an old computation which shows this, which is understand the Coulomb solution in this case. And then I will just sketch what I can say in linearized gravity. But let's say the main point that black hole entropy should have something to do with soft degrees of freedom, topological degrees of freedom, and not so much with physical gravitons. You can also understand in this context, you look in 3 dimensions, you look at 3-dimensional gravity, you have a black hole solution, the BTZ solution, but you don't have physical gravitons to start with. So the whole dynamics is in this sector in that case, which is of course also clear. And the last analogy I want to make is that the right observable to discuss, let's say, black hole entropy is the ADM surface charge, and the ADM surface charge is very similar to the electric charge, and it only involves, from the point of view of transverse traceless degrees of freedom, it doesn't involve transverse traceless degrees of freedom at all, in fact, in the linearized theory. Okay, let me not bore you with that. This is for a different audience. So in electromagnetism, you have, of course, the physical degrees of freedom, and you have this, in empty space, unphysical sector, which is the longitudinal part of the potential, and the A0 and the pi 0. And of course, you can decide what kind of quantization that you are doing. If you are doing a Berestey quantization, a Hamiltonian Berestey quantization, in fact, even in empty space, you can show that. So there is the physical sector with the physical Hamiltonian, but then there's the topological sector, which contains both A0 and pi 0, which contains the longitudinal part of the fields. And the Hamiltonian that you get when you build this, it is, of course, but it's important that from the electric field, you add the longitudinal part of the electric field to this sector, and then you can write the gauge-fixed Hamiltonian of this sector as a Berestey exact sector. So then you see that this sector is indeed a topological field theory in the definition of topological field theory, which says that the Hamiltonian is Berestey exact. So, and this sector contains the electric charge observable in the electromagnetic case, and it contains the ADM mass in the gravitational case. Okay, and of course, this gauge sector in topological field theories is typically indeed not trivial, and if you have non-trivial topology, if you have knots, if you have stuff like that, it can begin to contribute. So a very simple computation I did in this respect 10 years ago when I was trying to understand that, before I was able to count something and compute the partition function, was to try to see how the picture changes in free electromagnetism when you couple the simplest kind of source to the theory that you can imagine, meaning that you couple, you look at the electromagnetic field, you couple a point particle at the origin, which is just sitting there, and you quantize the system in the presence of this source. So the only thing that gets modified in this context is the Gauss law. And when you do Beer-State quantization, what you see is that the Beer-State charge just changes by the fact that your creation and annihilation oscillators, the A and the A dagger, which in this case are null oscillators. So I have this, so there's the physical, let's say, the bit of the transverse oscillators, and then for the longitudinal and the temporal oscillators, I use a light cone basis. So these are the oscillators A and B in the theory. I'm sorry to say that I think yes. I'm not sure. I don't need it actually. It's fine like that. No, don't worry. Perfect. Thank you.
Up.
Yeah, don't put. Yeah, okay. And where is the pointer?
The star.
This one. Okay. Very good. Thank you. So it turns out that then when you try to understand what is the Coulomb solution in terms of the quantized degrees of freedom, you find that the Coulomb solution is really a coherent state of these null photons. It's a coherent state not of the physical photons, but it's a coherent state of null photons. And so the claim is that this coherent state of null photons is really the quantum state that corresponds to the Coulomb solution, and the way you test that is you put the electric field in this expectation value, and you check that it gives exactly the right radial electric, longitudinal electric field that you are expecting. So this was a computation, of course, an easy computation. Well, I did 10 years ago, and I was never able to count the degrees of freedom in this case, because this is a kind of microcanonical situation where I fix the electric charge. So you really need these two plates to be able, with boundary conditions, to count something and to talk about degrees of freedom. Of course, then it was pointed out to me that this is, of course, not original at all, and versions of this exist since a long time. So, for instance, when you look back at Fock and Podolsky's explanation of Dirac's computation of the Coulomb solution between two non-relativistic electrons, it's basically the same computation. When you look at this paper, you understand, unfortunately, one cannot read that everything comes out of the A0 oscillators here. Nothing comes from transverse oscillators in this computation. So you have these two non-relativistic electrons which interact through the potential, and everything comes from the A0 oscillators. No, you can give them a time dependence if you want. Yes. No, as I tried to show you in the plates, it's not constrained. The longitudinal guy is not completely constrained. So that was the point here. You see, that's why I was careful to do this argument here. So This guy also should be constrained. It should be longitudinal, but it's not, because it's topological. It's not really longitudinal when you do the computation.
It's not really
And no, look. I did the Dirac analysis of this with this boundary condition. You see that these modes that I'm talking about, I mean, the longitudinal part or A0, they belong together in this sector. You can gauge change and put one into the other if you want. So if you look at the constraint, it does not involve these modes. It does not involve this specific zero mode. So that's why I was doing the analysis in these terms. You put it in the constraint, you put the mode expansion in, and you see that it's not affected by gauge transform. I'm just doing Dirac analysis for the system, in fact, with the boundary conditions. And then this thing is left over. And it is physical, exactly like in three-dimensional gravity. When you put boundary condition, you have a leftover two-dimensional conformal field theory, Wessumino-Witten theory. It's the same leftover, if you want. That should not be there if you have trivial boundary conditions.
With trivial boundary conditions.
With trivial, it's not there. Exactly. But with non-trivial boundary condition, it is there. That's the point. But indeed. But you see, in here, it's the problem with, you have non-trivial boundary condition because you put this source at the origin. If you put this source at the origin, the topology of space is no longer trivial, and you have something.
It's the Euclidean source.
Yes, but it's how you see it in the electromagnetic field. Because I only measure the electromagnetic field, and I'm not caring about the source. I want to see everything in the electromagnetic field. I also want to see everything in the gravitational field. Of course, I agree with you. It couples exactly to the source, but it captures the information of the source. And when you look at how they did the computation, that's how they did the computation to reproduce the Coulomb potential, Dirac-Fock-Podolsky, from the A0 oscillators in that case. Okay, that's...
You know why I stress this point? Because now there is some kind of clutch with this longitude.
I try to do the simplest possible system I can, where I can argue about these things with computation and not with intuition, if you want. But of course, it's free field theory. But still, in that case, you can do Dirac analysis. And then it was pointed out to me by this is really a pain. This is a pity that it's not readable. But it was pointed out to me by Stefan Theissen, who tried to repeat the computation for the gravitational field, that this computation was already done by Bronstein in the very first paper on quantum gravity, in fact. When you look, so Bronstein repeated the computation of, he tried to reproduce Newton's law between two masses, and he tried to reproduce the Fock-Podolsky computation in the gravitational case. And when you look at his computation, you see that in his computation, the gravitation, the Newtonian interaction comes only from the H00 oscillators. Not from any transverse traceless oscillator, only H00 is there. It's the same computation, that's what I'm trying. It's the same topological sector that gives this contribution. That's what I'm trying. So, from this point of view, it's not a new result, but it puts a spin on. So if there is sources, topology, or this thing, and you want to measure something only in the electromagnetic field, you have to be careful of the A0 pi 0 of the longitudinal sector. That's my only claim. Good. And for linearized gravity, of course, nothing changes. In linearized gravity, the analog of the electromagnetic Hamiltonian is the Pauli-Fierz Hamiltonian. This only depends on the transverse traceless fields. But then, you do the degrees of freedom in the Hamiltonian way. Either you look at this ADM paper, and you find that this is the physical Hamiltonian, only sensitive to at least naively, you only see the gravitational wave contribution, but then when you couple a source to the theory, so this source plays the role in the linearized theory of the black hole, obviously. I mean, just when you're far away, you see that this source only excites the trace degrees of freedom. So absolutely no transverse traceless degrees of freedom. And what measures this source? What measures this source is the ADM mass, and the ADM mass only also has longitudinal piece inside. So my claim is that even in this case, if you have non-trivial boundary conditions, if you have a source in the theory, you want to measure, you do a partition function, you have to be careful about the contribution of this bit to the partition function. That's all I am saying. Very good. So I hope I have convinced you that in the simplest model there is an interesting, nowadays it's called edge dynamics, but that doesn't matter because, there's a part of electromagnetism, the gauge sector, which is a topological part and which will contribute in topologically non-trivial situations. And of course, to some extent, I hope that some of it can be extendable to gravity to say something in that case. But that's, for the moment, I can do linearized theory, but this I can do in detail. At least I have convinced you that's the case. Okay, thank you. The microstates that contribute is the ones that you think are longitudinal. So this K3 0, this K3 equal to 0, 0 mode. Well, you very good, very good. You quantize these oscillators, and the Fock space of this thing are the states. The Fock space of the oscillator of this two-dimensional free particle is the microstates of this part of the theory. It gives the thermal contribution to the Casimir effect, going like the area and this kind of thing. That are the states.
No, I'm not talking about Casimir.
No. The states, again, good. So in the classical theory, you have Neumann condition. You can do it on, okay. And then the zero mode of that is a two-dimensional free scalar, and which you can quantize. You do the Fock quantize mass. Sorry?
There are states.
Yes.
Exactly, right?
Yes, there are states. You quantize a massless scalar in 2 + 1 dimension, and you do the oscillators for that thing, and that and the Fock space of the.
What are the energy spectrum? What is the energy spectrum of this?
You can see.
States are states, right?
Yes, yes. Well, yes, they have a Hamiltonian. You compute a Hamiltonian from the longitudinal part of the electric field in the original Hamiltonian. I have shown you. It was there. It's the energy of a massless scalar. It's the Hamiltonian of a massless scalar. So it's omega k squared, except that it's one dimension less. I can show you the Hamiltonian. It's a free massless scalar in 2 + 1 dimension with the standard Hamiltonian, but in 1 dimension less. And it's the geometry which fixes this. This is the guy that you have to quantize in addition.
So you can excite these states, right?
Yes. If you heat, yes, yes. I mean,
If my charge is 0,
yes.
still can excite
Yes.
the state between the planes?
These additional ones, yes. If you heat this thing up, yes. It contributes to the finite temperature Casimir effect. You can interpret one of the terms that they get from the modex, but it's the same computation. They contribute to that. I see you are not convinced. I was hoping. But why not? Is it because it's a computation, it's not interpretation? Okay, thank you. I was not even trying, I was really trying to have the simplest situation where I can do the separation. Of course, this is important when you have more complicated geometries. Then you need more invariant things. But it was the opposite aim. I wanted the simplest geometry where I can control this zero mode sector. No, the division depends on everything. I mean, in the spherical case, you have the zeros of the Bessel form. You have to see where they sit. So it's real work. That's what people usually are after. But then you lose this very simple picture, I would say. But still, I mean, basically it's still the same.
I think I have a question about the connection between your example with plates and your example with charge.
Good. Well, the example with charge, okay, there was exactly also one particle in addition, if you want, in that case. In that case, of course, you just have a line, or in the case of Fock and Podolsky and Dirac, you had two lines. But I have two plates, which is better because it makes this additional sector a bit bigger, if you want. I think you see the particle. I have not done the computation. We can maybe try to look at it, but I think you need to see the particle indeed.
I have two questions related. First, we will start analyzing gravity in the edit conversion to the modular gravity.
Sorry, in the Eddington version?
I mean, the determinant is 1 for the method.
Okay.
Which actually gauge the way some gauge degrees of freedom, which is locally equivalent to usual gravity. But I'm not sure it is equivalent in terms of non-trivial boundary conditions. So that's
then this picture would change. I mean, if you would do it, yeah. In my opinion, if you put non-trivial boundary conditions in both theories, you have different results in both theories, I would say.
And another question which is related to somehow. I mean, is it possible to distinguish between these topological degrees of freedom and physical degrees of freedom by some mechanism like localization?
Like what? Like?
Localization. Where, I mean, is there some heuristic operator that will distinguish between the just to write the answer in terms of cohomology?
This was an answer in terms of cohomology to some extent, but I think, well, I think what you are asking is, are there topological field theory methods which give this result? Of course there are, but somehow, sometimes they obscure what the degrees of freedom are. I wanted to do the converse. Of course, the result you can get much more quickly by using topological field theory results, I would say, zeta, if you apply them well. But here I wanted to do the converse. I wanted to see really the Hilbert space explicitly. And that's why it only works in the simplest geometrical case. But I agree. Of course, after you have understood what the degrees of freedom are, you can forget about it and you use the most powerful method to do the computation that is available to you, of course, right?
Okay, I think we need to go to the discussion. So, very 1 minute break, and let me kind request to switch off the sound of the record. Otherwise, the next picture is
Does it work? Он включен? Включен? Okay. Okay, so it's a great pleasure to speak here. I'm going to speak about this recent work I've done in collaboration with Amit, who is also here. And I'm going to speak about this first principle derivation of a holographic model in the simplest possible setup, where still things remain quite non-trivial. So the aims of this talk is to give some precise example of where holographic dual at large number of degrees of freedom can be derived, and just to give some probably introduction, should say that so there is a general belief that if you have some conformal field theory with many degrees of freedom, if you take number of degrees of freedom to be large and possibly also take some parameters to infinity, then you should hope for something nice to happen, and this is what is called holography in general terms. Of course, everyone has its own definition of holography, but I will stick to one which is has some practical implications, hopefully. So the aim is to get some derivation, because by far all these statements were at the level of conjecture. Of course, no one doubts some particular cases of holography, such as the duality between n equals 4 superyoung Mills and the string in the curved ADS background. But still, the derivation of this fact is absent. And this stops at, of course, I mean, when you have n equals 4, it has lots of symmetries. And then when there are only like one model with such symmetries, it's kind of simplifies the life if you want to conjecture some duality between two theories. If they have the same symmetries, you are done. But imagine a situation where there are no supersymmetries, then there is no really guiding principle how to build such dual models. So there should be some method which would allow us to derive something. And all right, that's a slide with citations. Just to mention that I'm going to speak about a particular type of model which generates a particular type of diagrams, so-called fishnet diagrams. And those were studied, so actually the term was invented in this old paper, and then integrability in these diagrams was demonstrated here. But today I won't speak much about integrability, just a little bit. So it's not really crucial for what I'm going to say. And right, we all have to remember the contribution of Peter West to the n equals 4 superyoung Mills. Right? Anyway, so the model which I'm going to deal with today is very simple, right? So I want to take something simple where we can do the derivations, and such model is this model. As you can see, this is in 4 dimensions. There are 2 scalar fields, which are n by n matrices, and the only interaction is of this form. So it looks like phi to the 4 theory. However, I mean, one of the features or of the theory is that you can see immediately it's not really very real Lagrangian. So, but let me list some features which were studied quite recently. So it's, first of all, it was shown that this theory, at least in the planar limit when n goes to infinity, and then is the size of this matrix, the theory is conformal. So probably it remains conformal even at finite ends. Then furthermore, it is integrable theory in the same sense as if you heard about n equals 4. There we can compute lots of quantities non-perturbatively thanks to this integrability property of n equals 4. So the same applies here. The theory is, even though it's 4-dimensional, field theory is still, you can compute lots of quantities exactly. Then it doesn't have supersymmetry, so it depends on your philosophy. It's either good feature or bad feature. And finally, it's also non-unitary, which could be also considered as an advantage, because if we want to build some method of building the holographic duals, we should rely on as few features of the theory as possible. All right, and today I'm going to show in which sense actually it's holographic and how to derive it. All right.
There is double trace terms.
Yeah, so I didn't write them. So indeed there is a double trace term with its own coupling, which is actually running coupling, but we've shown with Grisha and Volodya that there is a fixed point, and this fixed point is where the theory is actually integrable, and you can reproduce results assuming conformal theory. So it is conformal and integrable at the same time, and we checked it up to 7 loops with explicit calculation, so there are very little doubt that there is something wrong. Just didn't try them because they won't play any role in this talk, and furthermore, they're only needed for the at the perturbative level. So, well, it's not even real, right? So Lagrangian is not even real. So I mean, but also this conformal point is not real. So that's.
But can you just put real part?
Yeah, well, I can, but then I can solve it. That's the problem. Yeah, so the good way of putting a real part is to actually extend. I will show this theory is a part of n equals 4 family of theories, which obviously this one is not supersymmetric. And n equals 4 is conformal. It's just particular limit of a conformal theory. All right, so let me roughly summarize what's important from n equals 4. So n equals 4, what is just f mu square, some 6 scalar, three complex scalars, and actually 4, right? Oh, always miscompute them. So then we have some other fermions and so on, which is not so important. And today I will focus on a particular sector. I just call it U1 subsector for the reason, I mean, it's not the actual name used in n equals 4, but this is the sector which contains phi 1 to any degrees and any number of derivatives. And then phi 2 and phi 3, they have to neutralize each other. So it should be Dagger probably. Right? So they come in neutral combination. So there is only one U1 from R symmetry which survives. So these are the operators I'm going to consider. You see it's a huge class of operators. They could also sit at different points. So it's a huge sector. Right, and then what we know about this model and about the sector in particular is that the dual description can be given by a string. So X is a worldsheet field in 2 dimension, describing the worldsheet of the string. And then this term is here just to impose that X squared is minus R squared, so it's on ADS, right? So X squared belongs to ADS space. So signature is minus plus 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 plus. And then this is what's left from S5 in this sector because it's only circle, right? S1 remains. So if you want this ADS 5 times S1, right? Because today I will actually discuss the classical part of the story, and then Amit will speak on Wednesday about the quantization. All right, so what is the point of this dual, right? You can write them on the board, but why do we care about this? So one of the things why it's so nice is that you can find classical solution in the section. This will be some string moving, classical string moving in the curved space of ADS, so it's like hyperbolic thing. And then if you compute its energy, it would match the energy, the dimensions in n equals 4 in the limit when the coupling goes to infinity. Right? So if you compute at the same time, if you can do that, right? So if you compute a dimension of some operator exactly, then take lambda as a coupling to infinity, then prediction is here for you. It will match some string solution classical energy. So that's one of the applications. This is a picture stolen from Kostya, right? But the whole thing is more like Moldasena, right? That's because I gave first talk in Ardita, so I had to like be nice. Well, I'm nice in general, so don't take it wrong. Anyway, so you can do the same with correlation functions. If you have a like 3-point correlation function, you can again find classical worldsheet solution with certain boundary conditions. And then the classical action, or like area in this case, on this classical solution will give you asymptotic behavior of the amplitude when coupling goes to infinity. Right? So this is actually a practically useful thing because it computes for you asymptotics of energies and asymptotics of correlation functions when coupling is very, very strong. And this is so great because strong coupling normally is very hard to compute anything, right? That's why we love it. So the goal is then to build something like that for our Fishnet series. So, and these two theories are related. So related in not totally trivial way. So you have to do a certain deformation. So in n equals 4, you have this interaction term, which is totally real, right, so far. And now you can, so it's just a commutator of scalar square. And you can now deform it by introducing these scalar factors, which are conjugate to each other. And then what you can do, you can now play with these parameters and take the limit lambda goes to 0, but in such way that lambda times this factor is finite, right? And call this psi. Actually, there is some 1/2 missing, right? But who cares? So we want to keep this combination finite. So this term survives, but then this exponent goes to 0, and so this term is suppressed. That's how you get from n equals 4 to our Fishnet simple theory. So now we can speculate. Okay, let's just take the dual description and try to take this limit in this dual theory. So, but immediately we see the problem is that lambda plays the role of 1/h bar in this dual description, right? So the classical limit corresponds to lambda infinity, and we are taking limit lambda to 0. So basically, this becomes totally useless. Yes?
So is it, what happened with gauge fields?
With gauge fields, so they just get decoupled, so they become free. They are not coupled to fermions. Yeah, because lambda is suppressed, so they just become free. So there are different versions where you can keep some fermions and some supersymmetry on board, and also take the same type of limit. So there are. Volodya will probably speak about that on Wednesday morning.
The reason why they decouple because they're not looking at it. Then, because if you take lambda to 0, you still have free theory.
Yeah, you have free theory, right? Okay. But it decouples, right? Yeah, well, of course, we have Sasha here to compute correlators in free theory. Okay, it's a bit mean joke, but anyway. So they decouple, right? So the actual MITI bit is only the Fishnet. Okay, so as I said, so this limit is a bit tricky, right? You can't really do that, but let's still try to send just to get some inspiration. Of course, the expectation is it will be complete nonsense, right? Probably. So let's do this rescaling because we want actually psi, our new Toft coupling, to replace this old lambda. And if we do this replacement, then also the radius of ADS, you see, it gets rescaled. And so in this limit, you can say, in other words, that lambda to 0 is the limit when the radius of ADS goes to 0. Right? So that's the limit when ADS collapses to a light cone. And also the same, actually, here should be lambda as well. True about S5. S5 will also collapse to a point. Right? So the expectation from this naive limit is that we should get something on a light cone. And we'll see whether it's true or not. OK. So now let me formulate the problem for you. So given this 4-dimensional action, much simpler than n equals 4, that's all you need to know. Forget about double traces. They are relevant non-perturbatively. You have to find a dual description such that it starts from psi, and then there is some kind of stringy type of thing afterwards. So So first, you can ask, okay, for n equals 4, this works. We know it works, but maybe it's like the whole thing is wrong. This holography idea, like maybe it's nonsense, right? Why do you believe it? So we gathered some data, right? So as I told you, this theory is kind of integrable. So in particular, this allows to compute dimensions of operators, such as like trace of phi1 to any power, or trace of phi1, phi2, phi2 dagger. Like any local operators, you can compute. It's not totally trivial, right? So you have to solve some Baxter equations and impose some quantization condition. And it's impossible to do analytically, except for like V-coupling expansion. And then if you look at the V-coupling expansion, you get a bunch of multiple zeta functions. So it's quite complicated. But nevertheless, you can get this picture, which is you can see anything, I understand. So this is psi, right? This direction. It's 3D plot because this is imaginary part of delta, because it's not a real theory, and it's not a unitary theory, and this is a real part of delta. So you see that when psi goes to 0, you have operators with integer dimensions, right? And then when you increase your coupling, all these loop effects, they resum into these nice curves, and then they have some branch points and so on. But the lesson from this picture is that states, they actually scale as psi, right? So which signal to us existence of the classical description. And also you can find by computing this correlation function, which we did with Volodya and Grisha recently, if you well, maybe not that recently anymore. If you compute this correlation function, and again, we can do it exactly, but not using integrability, using just these methods in BFK, this resummation techniques. You will find, with actually lots of struggle, that it's a strong coupling. It behaves also exponentially with some coefficient, and we have prediction for this coefficient and some, and indeed it is some tunneling process. Classical looks like a tunneling process if you want to interpret it. So it all signals existence at strong coupling, some dual description. All right. So what's important to understand before I start? Any questions actually so far? Question?
You started from unitary theory. How it became non-unitary?
Well, because I took parameter complex, right? If you start a uni, yeah, if you take coupling constant imaginary. Well, I mean, any theory is not unitary if you take coupling constant not real, right? So, any more questions? Right. All right. So, what makes the theory simple? So, and what is not true about n equals 4 is the structure of diagrams is very simple. So, because there is only one type of vertex, it's like black line, which is phi1, and red line, which is phi2, they can only cross with one polarization. So arrows should match. It's only this and this arrow, which exist, which implies that, say, correlation functions of this type of operators should have the following form. So you have this phi2 dagger, and then must annihilate. So it's like a big bang here, right? So it creates lots of particles, antiparticles, and after some time they all annihilate. And then what's left after you get rid of antimatter, you just have this wheels, right? So main part, the meaty part of the diagram are these wheels. And this wheel you can kind of resum using some operatorial approach. So let me introduce this integral kernel B.
What was black? What was red?
So black is phi1 scalar, and red is phi2 scalar, right?
External points are...
Yeah, so I have these two operators, phi1 to 7, I don't know, right? Phi1 to 7, and then I must connect phi1s directly, and then in the loops it's only phi2 which can move around in the planar limit. Right. Right, so you can add, you can observe that each of these wheels can be added by action of this integral kernel, right? So it's quite standard in BFKA or, for example, is to introduce this kernel. So what is this kernel? This kernel, you can see x minus y. You can see anything on this picture.
X is a complex or real number?
No, this is Feynman diagram, so you integrate. Yeah, this is the usual integration over flat. Yeah, everything is, actually the separator is self-conjugate even. Probably it makes it nice to mention. So x minus y are these little propagators going outside. And this y minus y are these links connecting this. So you see this b, when you multiply your diagram by this b, it will just add your extra ring of red and extra things going out, the black ones, right? And then what you have to do, you have to integrate in coordinate space, you have to integrate over new vertices, right? That's how the separator acts. So, and then you can say the main bit of this diagram, it comes from like 0 wheels, 1 wheel, 2 wheel, and so you just have the separator to the power n, and you have to sum them together, and you get a geometric series, and then you can say that 2G correlation function of, say, phi1 to the j, and phi1 dagger to the j, is just given by a matrix element of this formally written inverted 1 minus b. Okay? Yeah, about this one. You mean the first propagator? Yeah, okay, yeah. Well, I also have to add, no, first one. Yeah, okay, I simplified it. Yeah, I need to add the first propagator. So there is also some constant. But the main dependence on the coupling, you see, it sits in B. Right, so the non-trivial dependence on the coupling sits in B. All right, so what is like, okay, this looks very nice, but totally useless because B is some integral operator. How can you like invert it, right? Good luck with that. So of course, it would be nice if you could diagonalize this B, then insert the complete set of wave functions and replace B by its eigenvalue. So fortunately, in general case, it's impossible to do, but let me demonstrate how to do it in particular case when there are only 2 phi1s. In this case, you can use the property of this B, that this B actually commutes with the whole conformal group, right? So it's obviously rotation in translation, but also the special conformal also commute with B. And so the wave function must be an invariant tensor in the, covariant tensor in the conformal group. So it's like highest weight state, for example. So then from this, it's completely fixed just by this expression, right? So there is nothing else you can write. And the eigenfunctions are parameterized by 2 parameters, spin and delta. And delta is completely arbitrary number. No matter what delta is, you can show that B acting on psi is just an eigenvalue times psi. And you can compute this E. So how do you compute it? You have to act with B and integrate an x1 and x2, right? So it's 8-dimensional integral. But fortunately, these are just star triangle integrals, so you can compute them quite easily. So and then what you get for the eigenvalue of B is this expression. Right, so now notice that delta so far is completely arbitrary, it's just a parameter of this wave function. So what you have to do, you have now in simplified terms a little bit, you have to insert the complete set resolution of identity here in terms of the eigen vectors and replace B by the eigenvalue. So at the end you get this expression sum over spin, then integral over delta with actually some measure which follows from conformal symmetry. So there will be integral over this continuous parameter and then this standard part which you can compute. So You see delta is not anything special, so you'd expect at this point maybe delta has something to do with the dimensions of the local operators. And in fact, it does have to do with them if you observe that this integral has poles which are coming from e equals to 1, right? If you pick these poles, instead of integral, if you write it as a sum over the poles, then you actually recognize the standard partial wave expansion of the what? What? OP, okay. OP expansion of a 4-point function. Right, so G is just the conformal block, and C is the residue at this pole, which gives a structure constant. Right, and after you set E to 1, what time is it? It gives the interpretation delta is fixed, delta become a function of S and Psi, and this reproduces the dimensions of some local operators. Right, so before delta was a parameter, once you sit on the pole, it actually becomes a function of your coupling. Right, so this is how results look like. So there are two actually states. And if you expand that V coupling, you see there is like 2 and 4. It starts from integers. And then there are the slope corrections, and you can check a couple of them perturbatively. And also you get from this calculation the structure constant. Oh, something happened to this plot. And OK, let me not spend much time on that. So this is the data which we have, right? So and now my point is that if you take the strong coupling limit, you see clearly that delta gets this classical type of behavior you normally see in string theory. So delta, the energy would scale as 1 over h bar, as in any classical model. And furthermore, the structure constant, the 4-point function, is exponentially suppressed like that, where theta and rho are some cross ratios of this 4-point correlator. Any questions? No? Is it what? Yeah, well, so there are some like small detail about completeness, but they all dealt with in a good way. Because furthermore, so we checked this expression up to like 7 loops, as far as I remember, maybe a bit less. So it's Euclidean.
But since you don't have unitarity in Minkowski space, this will not satisfy the usual requirements of axiomatic approach to Westerwalder-Schroeder conditions.
Yeah, of course. So all the theorems which use unitarity, they like have to be improved, let's say. Yeah, improved by discarded. Yeah. Right, so okay, these are 2 pieces of data I want to reproduce, and so I want to build some classical model which would actually give me these results, right? So you see, actually initially we wrote in cross ratios, it was very ugly, and now actually it's, okay, it's due to this result.
So your definition of exact result is summation of finite diagonals?
Yes. Or do you have the different definition?
Do you have some non-perturbative correction which I know?
Well, it's planar limit. I believe, like many people believe in planar limit, it's kind of not very important.
Depends on what?
Well, this is my definition of the theory. Given a classical action of Fishnet, right, compute all diagrams, resum them, that's the complete theory, it doesn't need anything else. Right, normally you don't add non-perturbative corrections by hand. Right? You clearly see some series is asymptotically convergent. Here all series are absolutely convergent. Yeah. Yeah, they are convergent series, so why would we bother with non-perturbative businesses, right? I mean, You know how it works. If it doesn't work, then you add them, right? Anyway, so what we have? So we indeed have energy scales as 1 over h bar. Correlation function is indeed some tunneling process. So we need to find what lives on this worksheet or whatever replaces it. All right, so let's now start the derivation, right? So our starting point is this B, the graph building operator. So we realize that the states corresponding to local operators, they come from this point when B is 1, right? This is what gives us pole in denominator. So the wave function corresponding to the states of local operators, they should be this B minus 1 equals psi, right? So now, I mean, B is an integral operator, not very nice to deal with. So let's do the following obvious trick, which like performed before us many times, of course, is let's take this equation, act by a product of Laplacians on it. Because Laplace operator would kill this term, it will create delta function instead, and delta function will remove the integral. After that, it just becomes a multiplication operator. And the price to pay is that instead of identity, you get a product of Laplace operators, right? So at the end, that's what you get. You get this equivalent way of writing it is H is a product of Laplace operators or the Lambert operators, never know, right? And this B itself becomes just this type of potential. And we have condition H on psi is 0. So H on psi is 0 could remind you something. Yeah, Arkady is not very happy with that, but hopefully it will improve. So this reminds of something, right? H is 0, it means time reparameterization symmetry, right? Because if you think about H as a Hamiltonian for a second, then it means that wave function doesn't depend on time at all. So if you change time to any function of time, it's still the same, right? So your theory is obviously time reparameterization symmetric. So you can find the same type of condition, H is 0, in string theory, right? If you start from this, what is that? I forget. Nambu-Goto action, right? And write the Hamiltonian, then it's also a 0, right? That's the constraint you get. So let's act an analogy. So let's take H kind of seriously as a Hamiltonian, try to write the corresponding Lagrangian, right? Just in a classical way, right? So I'm discussing classical theory. So if I do that, of course, I mean, you have to do dH, dP, get x dot, and then plug it back, blah, 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 blah. And then you get this ugly power. So first, it's not a sum of kinetic terms. It's like a product. And the top of this, it has some ugly power here. But we can also insert this gamma, because as I mentioned, there is this time reparameterization symmetry. So if I replace t by f of t, it will create me this f prime, right, in this term, and 1 over f prime in this term. And you can think about h being 0 is just equation of motion for gamma. The same way as you have in Polyakov action. If you take, if you write equation of motion for the metric, you get h equals 0, the Virasoro constraint. Right. So that's our Lagrangian, right? So now what we can do, we can make it a bit nicer, because this is not something we would be happy with to end up. What we can do, we can take advantage of the time reparameterization symmetry of the fact that gamma could be anything, right? So let me take the gamma which extremizes the section, right? Gamma could be anything. So I find the one on the extremum. That's what you do when you go from Polyakov to Nambu-Goto action, right? So if you start from that, extremize it, and set, oh no, I'm not doing that. Yeah, I am doing that, right? And extremizing gamma, you get this section. So so this reminds really Nambu-Goto action, right? Just instead of square root, you have 2j power, and otherwise it's quite similar. And then it's a product over my particles. So this product over how many phi 1s I had in my correlator. So still quite ugly, but let's look at this in a positive way. So it has time reparameterization symmetry, obviously, right? Because that's exactly the power which would cancel the factor from dt and from x dot. So it has rotation translation in X. And, I mean, maybe not too surprisingly, it also has special conformal, actually, symmetry. So what we are going to do next is to try to make this special conformal, the whole conformal symmetry, more manifest. So and there is a standard way of doing that, known from the times of Newton, according to Amit, right? Is to introduce this X, six-dimensional vector, such that its 4 components essentially coincide with initial 4, right? And then you have a condition x squared equals 0, and you also divide by this x plus, right? Then you can check the following identities. So first fact about this reparameterization is that special conformal become a linear transformation on this capital X. So all conformal group, which acts on small x in an ugly way, becomes nice in terms of capital X. And then there are these identities, which are trivially follow from this. Let's not waste too much time. So the fact is that our initial action takes this form in this capital X. So now we see conformal symmetry is manifest, because, I mean, this is just scalar product. Obviously, it's invariant under rotation. So, but there are some news. So time reparameterization is still there. Conformal symmetry is now manifest. But we got a new symmetry. We can rescale each x with an arbitrary function of time independently. So xi goes to fi xi. So why is that? Because x squared is 0, which means that x dot is 0. So which means that if you change f to f of x to f of x, you must pull this f outside. Dot cannot end up on f, right? Obviously. Because then you get 0. So these factors of f in numerator and denominator, they happily cancel. So you get independent new rescaling, new gauge symmetry. So you have j plus 1 gauge symmetries now. You have time reparameterization symmetry and rescaling of each of x's. So what we can do, we can now treat it in an inverse way and Polyakov these gauge symmetries, right? So meaning that we introduce the corresponding field for each of these gauge symmetries, and then we disentangle this action into this action. So the relation between these two is the following. If you, so you can set lambda to anything you like by rescaling x, right? So lambdas are completely up to you. So in particular, if you set lambda to the extremum, sorry, I don't know, it looks like lambda a little bit, right? From far away, but obviously I'm not far away, so it's a fair comment. So if you set alphas to the extremal values, then you get back to the section. It's not like maybe, I don't know, depends on how intense your training was in classical field theory, but if you believe me, that's what happens. So if you extremize in lambda, in alpha, my neuron responsible for alpha died apparently this morning. So if you extremize in alpha, you get back to the section. But also we can take advantage and fix the gauge in analogy with Polyakov, right? We can set all these alphas to 1. Yes, it's alpha. We can set all alphas to 1. So and after that, we get this action, you see? And now what is nice is that kinetic term become really disentangled. It's very nice. It's local. Then potential is whatever it is. And then you can also introduce Lagrange multiplier to fix the time reparameterization symmetry in this way. So it looks like a radius of ADS, but of course R at the end of the day should be 0, because x squared is 0. So that's the dual action I claim. And one feature.
Sorry, I can't hear. So how now you can find it R?
No, it's not finite. It is just a Lagrange multiplier for eta. but you have to set it after you derive classical equation of motion to 0.
I see. So R is not element of it, but we will see it in it.
Yeah, this was like kind of a joke, but I think it's funny. So you actually, you can say R squared is a Lagrange multiplier for this gauge condition, so it looks like radius, but actually it is 0 classically, right? So what Amit will be telling about is, speaking about is that actually due to quantum correction, this radius become non-zero, but this is a quantization story. So okay, so this is our classical action. And what we probably, I forgot to emphasize, is that actually psi, after all this transformation, psi appears in front to the perfectly power 1, right? So it's like as we wanted it to be, psi plays now the role of 1 over h bar. So it's just convention is a bit stupid. I forgot psi probably here. All right, so we of course have to remember about constraints coming from this gauge fixing, which is analog of Virasoro constraint and the conformal gauge. Then equations of motion are quite nonlinear. Actually, it's beneficial to choose a gauge where lambda is 1. It's possible, then it becomes very explicit. And then, obviously, there are these global charges, conformal symmetry, which are now defined in a totally standard way. And then dimension appears to be one of these charges, and then spins are others, like diagonal parts of this cube. Okay, so this is, how much time do you have?
7 minutes.
Woo, lots of time. So that's the end of the derivation. Now what I want to do, I want to test this, that we didn't do any stupid algebraic mistake, and test this works actually, right? So in other words, that we will be able to reproduce all the data we gathered from exact solution in some particular case, but then this model is true in general.
Could you just summarize before you
Yeah.
So your claim is that you have your action.
Yeah.
You started with it.
Yes.
You restrict attention to a particular sector of operators, which are labeled by this J.
Yeah, so just for
Your
simplicity.
action applies only to the sector.
Yeah, it's so far to the sector, but like we have some ongoing stuff which may be published at some point.
So that would be the CFT in a particular sector.
Yeah, yeah. But it's like closed sector, as you would say, in this particular case. The perturbatively. No, from the perturbation point of view. So if you have this set of operators, you will never create in between something else.
Okay.
So good point. So what's the comparison with string? So you see we have j particles. It's not one particle. It's I actually j. So for each phi you have one particle. And then actually string appears, classical string become really classical in the limit when the j, which is the R symmetry charge, becomes large. So if you really want to compare to string theory, you have to take the limit when there are lots of such particles, and then it looks more stringy. But this model is better in a sense than string because it works even in the regime where the number of the charge is not that huge. It works for 2, for example, and for 3.
This is tension string.
Yeah, it is tensionless.
So this Lagrangian, if we go back to Gleb's lecture,
Yeah.
it's integrated.
All right, yeah, I have slide about this, yeah. I don't know whether I should go though to Gleb's lecture exactly. I don't know whether he mentioned this model, but maybe he did. It's interesting to see. All right, so let's now go through examples. So first, j equals 2. Let's build. So what we want, we have classical model. We just want to build classical solution, right? So and for 2 particles, you can always choose a frame where this first particle, the second particle, it has this form. Right? And furthermore, because we know that charges, the conformal charges, they of course commute with the Hamiltonian, we know that S dependence on time should be just proportional to delta, because S is essentially dilatation. phi should be proportional to the spin. And I mean, you have to choose time parameterization in a nice way. And then S, this S, that's important. It's probably a stupid notation, but this is actually action, you see? That's action on this solution. And action is proportional to psi, but also proportional to time. Yeah, so it's a simple situation where classical action is just linear in time. All right, so now you see it doesn't give any relation between delta and S. However, now we have to remember about constraints. When we impose Virasoro constraint, if you plug it here, you see you get something like delta square from this term, something like S square when you take dot of phi. And then you have to compute scalar product. And after all, you reproduce precisely this classical limit of the exact result. So for the spectrum, it works perfectly. So this is how solution look like. So you have two particles, and they're like spiral or spiral around, spiral, They spiral around like that, and also like go further away from each other. So now we can also actually ask ourselves, can we like reproduce 4-point function? And the answer is yes. So what we have to do, we have to now find a classical solution which starts at x1, x2, and then after some time it finishes at x3, x4, right? So I have to fix starting points and final points and tune the initial data in such a way that this solution goes. And then I compute the classical action on this classical solution. So there are only two parameters, actually, we can tune. If we fix the starting points, say, to plus minus 1, then we only have, say, delta as a parameter, because spin and delta are related to each other. And we also have time, the time of propagation. So there are two parameters exactly to match the cross ratios, theta and rho. So and then the classical action will become a function of this cross ratios, and that exactly reproduces what we got from this direct calculation. So this reproduces our result with Volodin and Grisham. Okay, so now 3 particles, right? So 3 particles, in general, you can't really solve analytically, right? Because it's like 3 particles, serious business. So that's how solution look like. You see they like start at some point because it's the highest weight solution, and then they like develop and go to infinity. So to actually visualize the solution, it's better to map it to a cylinder, right? So they just move along the cylinder with time. So if I do that, that's very conceptually important picture, okay? Because it's going to totally justify the name. If I run now, you see there are 3 particles on the exterior of a cylinder. And we clearly see that these particles, they behave like little fishes, right? They like approach each other. They like play a little bit, and then they wander off, meet another fish, play around. This is why the theory, of course, was called fish chain, right? Because it's a chain of very joyful fishes, right? Which like to play with each other. Okay, so now your question about integrability. So you can just open the book of Fadeev and see how the integrability for the torus works. So the way it works, you have to build this pair of matrices for each side. And then if L dot satisfies this equation, then it's pretty obvious that T, which is a trace of product of L's, will conserve in time. Right, so T dot will hit one of the cells, and the cell will get replaced, and then these terms will cancel in the shape. So anyway, so that's a standard thing. So if once you can find L and V satisfying this equation, then you are done. And in our case, we found that L can be constructed in terms of this Q. Q is this local conformal charge, which acts locally on your side. And V is a corresponding current, one could say. And so there are these equations. So that's the definition of Q. Q dot is a finite difference of J's, and J is this combination. So one can prove integrability immediately. So it is an integrable model if you know whose name it should carry. Now, I would accept it. If not, we will claim it for ourselves. So, okay, let's give time after the lecture. Right? Then it will be called after a meet. So let me finish. So there are some open questions after my talk. So first, all the manipulations I've done so far, they're purely classical, right? Because I was not paying attention to like operatorial nature of and so on. So what we can do, we can start from the section, which is kind of local standard action with constraints, and just quantize it in the canonical way, right? Like Dirac bracket and all this stuff. That's what Amit will be speaking about. Then, of course, the real challenge is 1/n corrections. That is where we expect, gravitons to start interacting and all this stuff. Then we can also explore integrability from this simplified model, because integrability of classical string was very useful, but it's mega complicated compared to integrability of this model. So then there are versions of this fishnet in 3D and 6D, so it would be also interesting to repeat the derivation. It's not totally obvious how to do. And Volodya will speak about the QFT side of this. Okay, and then, so because this model is related to n = 4, and in n = 4 we still actually don't have proof that it's integrable, right, apart from 3 level by Bizert, right, I don't know what it means. But in this model we actually have a proof of integrability, right, it's just kind of obvious. So also we now have derivation of holography, so we are learning a lot from this model, so now we can try to go back and take into account lambda corrections, which we discarded in this limit, and learn something about n = 4, and so on. So thank you for the attention.
Yeah, so you're describing it as this like, I mean, your model describes the vector of a string state.
Yeah.
How do yes, it's semiclassical string, you have to assemble many vectors. But do you have an argument that you will recover worldsheet deformations or not in this case?
No, we are not hoping to recover the string, right? It's not the point. No, I don't think the string wouldn't come from that, right? It will only come from that when you go back to n = 4. When you take into account lambda correction. It's not the feature of this particular sector that we don't have string.
Can you think about what would be the continuous transition from strings and the n = 4 to that?
Yeah, we are thinking about that, how to like add at least corrections so that we can approach n = 4 in like steps, right? But it's a long way, right, from corrections to actually coming there.
Can you describe scattering of the strings?
So you mean, yeah, so it's 1/n essentially, right? You're asking. Yeah, so you can have correlation function of some local traces, or you can have 2 traces with open ends, then we can do it straight away here. Just find classical solution with these ends and compute the action, as I did for j = 2. If you want 2 traces, yeah, you have to do this joining of string into a bigger fish chain and then like decoupling again.
But don't you have some extra light modes in the model which you have to exchange?
Well, I don't know, we didn't do that, right? Is what? So it is a strictly planar limit, so graviton is decoupled, right?
Is it possible to make gravity dynamical or
Yeah, this again relates to 1/n, right? I'm afraid.
and that can be done consistently?
Well, that's a hope, obviously, but we wouldn't try to do it inconsistently on purpose, right? So we will, of course, try. If we try, we'll do consistently. Yeah. I'm not sure if that's a question.
It's like it's a complex theory, so gravity is
Well, there is graviton, right? Still, in a sense, Lagrangian multiplet. Yeah. Well, it is conserved, it's protected.
Suppose you imagine that you try to perform the same procedure for the scalar sector of n equals 4.
Yeah, then you will stop immediately at the first step because you don't have the graph building operator there. So probably there is something like graph building operator if you had something like n equals 4 Feynman graph formalism, right?
Yeah.
Maybe you replace propagators with some n equals, but it was never done. Yeah.
Found out some operator and performed the simulation. You would arrive to the particle model again, not to strings.
Yeah, but again, it will be particle model when J is small. Then when you take continuous limit, because you see, in Fishnet we have tensionless kind of, so it's ADS is radius 0. But if you take into account corrections in lambda, which we dropped when going from n equals 4 to Fishnet, then expectation is it will be actual finite ADS. And then on finite ADS, you should be able to have a smooth limit when J goes to infinity. So then you can get just, as a continuous limit, you get a string.
How do you see the Euclidean line
Yeah. Yes.
dimensions will be complex. How do you expect dimensions? One theory is not going to be another.
So the B as a graph building operator is self-conjugate and its eigenvalues are real. But then when you pick the poles, then you actually have to choose upper half plane. And when you pick poles, they become potentially imaginary. So it's basically when you solve so we have a quartic equation, right? When you solve quartic equation, it's real until you hit the branch point and then it becomes imaginary. Yes. Yeah, I think the answer is again. So it's like in string theory. What you should distinguish between Hamiltonian and target space and worldsheet Hamiltonian, and that's when the transition between the two where you get it's non-unitary. Yes. Yeah, it's better to have it complex, but I think the question is if you keep it real, it looks like everything is fine. But I'm. Yeah. Yeah, it's exactly the same. It's the same story.